Text rendering is one of the most fundamental systems in basically every graphical application. It's something most of us take for granted when using libraries, but if you ever tried doing it yourself from scratch, you probably know that there's a lot more to it than just placing characters on the screen, whatever that means. So, in this video, we are going to go through all the concepts needed to draw text to the screen, all the way from the simplest methods to supporting multiple languages and scripts. This video is sponsored by Brilliant. More about them at the end. To start, it's always good to break down our problems into simpler ones before we start solving them. And in this case, before we can draw text, let's try to draw a single character. In general, there are 4 distinct ways of doing so. The end goal of any graphical application is to draw to something called a frame buffer, that is, a canvas made up of pixels. Every pixel is just a single color, generally stored as RGB or RGBA data. Well, since all we want to do is set the color of certain pixels, the easiest way of drawing some character is to define your character in the form of these pixels. Such a representation is called a bitmap and is dead simple to draw. All you have to do is map the texture in place on the screen, something that your GPU can do millions of times a second. That seems great and all until you try to zoom into the text or try to make the text itself bigger or smaller. The issue is that the bitmap itself has a width and a height, and deviating from that size means that you have to somehow either minimize or maximize the image when drawing. There's a super easy way of visualizing how this is done. We have a source bitmap and a region that we want to draw the bitmap to, which in this case is bigger than the bitmap. So you can imagine stretching the gap between the pixels to fill the entire destination. Now, zooming into a specific region, we have to figure out the exact color of these pixels in between. And there's 2 ways of doing so. The first is just to take the color of the nearest pixel from the bitmap, which results in a super blocky text. Not great. The other way is to somehow mix the colors of the 4 bitmap pixels in between which the current pixel lies. Generally, this is done through something called bilinear interpolation. Unfortunately, this doesn't work that great either, giving us this bad blurry image. Ideally, we want sharp text at any scale, but that doesn't seem possible with bitmaps. What all this means is that this technique is only really used in places where you basically never have to vary font size very much, or preferably at all. Obviously, though, it's not as though those constraints are possible in every application, which is why vector fonts were invented. In this case, instead of representing a glyph as a set of pixels, they're represented using mathematical curves and lines. If you want to learn exactly how a vector font is rendered directly using the common TTF files that you find, you should go and watch Sebastian Lake's video on the topic, because he goes through the whole system in a way I probably never could. But I'll just go through the cliff notes here. For a GPU, drawing lines is a very fundamental operation, so that part is taken care of. To draw the Bezier curves, you just have to decompose them into lines based on some resolution parameter. Or you can go the route of writing a shader for this, but I digress. This is also pretty easy to do overall. The tricky part is filling the character in, because to do that, you have to run something called an inside-outside test on every pixel in the glyph's bounding box. Essentially, at every pixel, you cast a ray in an arbitrary direction, then just count the number of intersections the ray made with the lines and curves of the glyph. If you get an even number of intersections, you know that the ray entered and exited the glyph while going to infinity. If you get an odd number of intersections, that means you never entered the glyph for the first iteration, which means that the ray started in the glyph itself. So, if you color all the pixels that yielded an odd number of intersections, you get an appropriately colored glyph. Well, that seems great, right? Since our glyph is defined completely mathematically, scaling it up just means scaling the space that it's in, which is absolutely no problem at all. Unfortunately, if it wasn't obvious by this point, this method is slow as hell. For every pixel in a glyph's bounding box, you have to do ray intersection tests with every curve and line composing that glyph. Doing that when drawing every character is just too slow to be practical, especially considering that drawing text to the screen is normally not the primary purpose of a program. Here's the thing though, when there is a specific part of a program that is slow to compute, and you know that you may have to repeat those computations multiple times, one of the simplest optimizations that you can make is to introduce a cache. In simple terms, you store the input and output of the slow part in some fast lookup data structure. So instead of repeating the slow computations from the input to get the output, you can just look up what you computed already. What that amounts to in this case is something called a font atlas. This is simply a big texture where you draw your vector glyphs to. Then you can use a simple texture map to draw the specific region of the font atlas, which is super fast as I described before. Basically, what we have done is converted a vector font to a bitmap font because it's faster to draw. This process of converting vector graphics to bitmaps is called rasterization. This method shines when you want to draw the same glyph a bunch of times because you only have to rasterize the vector form of the glyph once and reuse that output however many times you need. Although there's an issue with this method too. Resizing the font will look good, but with every small font size change, you will have to re-rasterize all the glyphs with a new size, and the rasterization is still not cheap. This is a particular issue in games and in-world text, where the player can move around however they want, and the text has to fit correctly in their perspective. In these cases, it's not great to use bitmap fonts, which are fast to draw but impossible to scale, nor is it great to use vector fonts, which are perfectly scalable but just too slow to draw and resize. What we need is something kind of in between, which leads us to this paper released by Valve in 2007, titled Improved Alpha Tested Magnification for Vector Textures and Special Effects. This paper outlines a method of glyph rendering called SDF-based fonts. Essentially, SDF fonts are like bitmaps, where a glyph is represented by a set of pixels. But instead of the pixels storing a color value, they store a value proportional to the distance to the nearest edge of the glyph. Pixels near the glyph's edge are around 0.5. Inside the glyph, we get values from 0.5 to 1, whereas outside the glyph, we get values from 0.5 to 0. By itself, this doesn't seem special, but the main difference is how you draw this glyph. Instead of directly mapping the texture onto the screen, we introduce a threshold value, where if the texture value is greater than that threshold, we color the pixel in. Otherwise, we discard it. By introducing this simple change, we can get rid of the blurriness that we saw when working with bilinear filtering on bitmaps, and it gives us a pretty good outcome. Looking closely though, there's very noticeable aliasing. To get rid of that, we can use the smooth step function and give it a small smoothness parameter to mix between the text color and a color with 0 alpha, and that gives us some pretty good looking anti-alias text. There's another big advantage with distance field based fonts, which is text effects. You can easily isolate particular distances in this SDF texture and color them differently, giving outlines, glows, shadows, and so on, without having to re-rasterize the glyphs, which is just great. When drawing the glyphs at a different size from the distance field texture, because we are relying on bilinear filtering, there's really no need to regenerate the SDF either. However, if you try to draw an SDF-based glyph at a scale that is much larger than the SDF itself, then the glyph will look a bit weird. It looks a bit too smoothed out in cases. Specifically at the sharp corners, the SDF seems to struggle at high scales. So, why does this happen? Well, this is again to do with the bilinear interpolation that I described earlier. Let's take the top corner of the character A as an example. For a small enough resolution for the SDF, we may have to sample these 4 pixels, and since all the 4 pixels show that they are inside the glyph, the bilinear interpolation between them will give us the gradient where we lose the small triangle which should be outside the glyph. Other such weird cases caused by bilinear interpolation add the unwanted quality loss at corners. So, how do we fix this? Notice, at the end of the day, what we want to do is be a bit careful with the interpolation that happens around such corners. Specifically, we can notice that to draw this right side of the glyph, we don't want this left side to weigh in to the interpolation. And similarly, when drawing the left side, we don't really want the right side to be there. This is the simple idea driving the fourth and final method of drawing glyphs, called MSDF fonts. The idea behind MSDFs is very simple. We take a glyph and split it into multiple sections at corners and assign a unique color to every section. The coloring is done in such a way that any corner will never have two edges of the same color. Generally, the selected colors are a mix of two RGB components, that is magenta, cyan, and yellow. Once you have assigned these colors, you can go ahead and generate the SDF in all the three color channels separately, giving you something like this. You can already see that parts of the image that are magenta, cyan, yellow, or white are inside the glyph, whereas red, green, blue, and black sections are outside. Drawing a glyph with this representation is super similar to the SDF rendering part, so let's bring back the parameters. The only thing that really changes here is the value parameter. Since we don't just have a single distance value anymore, we have three stored in the RGB color channels of our image. In the end though, we still need a single distance value, and to get that, we can use something called the median operator, which is the same as the median in statistics. Once we have this single distance value, the rest is the exact same thing as an SDF. I highly recommend reading the original master's thesis by Victor Cholomsky on the topic to know exactly why all of this works, because, for this video that's getting a bit too in the weeds, but it should be linked in the description. So, all of that was just to draw a single glyph to the screen, but obviously that's not enough. We want to be able to draw full strings, and for that there's plenty more to do. First things first, we have to figure out how a string is even represented in programming languages. If you have ever done any programming yourself, you've probably heard of ASCII. This is an encoding scheme designed by ANSI, the American National Standards Institute, back in 1963. All it is a defined standard that maps the most common English characters, special symbols, and other markers to regular odd numbers ranging from 0 to 127, aka a 7-bit number. This standard was later updated to use the full 8 bits in a byte, called the extended ASCII encoding. So, a string is just a set of bytes, where every byte directly maps to a single character. Many of the programming languages that were invented back then, like C, use this encoding to represent strings. However, there's clearly a problem with ASCII. Being invented by an American institute, the only characters and symbols supported are the most common ones used in the English language. Characters from other languages and scripts just aren't there. Not great if you want to render any arbitrary text. To solve this, a different standardization was developed, known as Unicode. It works pretty much like ASCII, where every character you can think of is mapped to a unique integer referred to as a code point. It's not just characters that have a code point, by the way. Emojis, character modifiers, marks, etc. also have their own code point. In this case, the range of integers that can be Unicode code points is 0 to 10FFFF, that is 1,114,111. This number fits within a 32-bit integer instead of a single byte. So, if we follow the logic of ASCII, Unicode strings would just be a list of 32-bit integer code points, and every 4 bytes would map to a specific character according to the Unicode standard, right? Well, yeah, that does work. But take a look at a simple string like hello world. There's so much wasted space here, mainly because Unicode is a superset of ASCII and the Latin alphabet has a value that fit in 1 byte. So 3 bytes are just left unused. This method of encoding Unicode strings is called UTF-32 and is the simplest method but also the most wasteful. To address this wasted space, a different Unicode encoding, UTF-8, was introduced. In this encoding, a single code point can be encoded as 1, 2, 3, or 4 bytes. The encoding itself is pretty simple beyond that. The number of leading ones in the first byte tell us how many bytes the code point takes. And beyond that, it's just a bit of bit fiddling to get the actual code point from the encoded UTF-8 form. Now, the hello world looks much more compressed. There's another way of encoding Unicode strings called UTF-16, but it only exists to keep compatibility with an older Unicode encoding format called UCS2. Anyways, with that out of the way, let's get back on track to actually drawing these things. We'll assume that we have a list of Unicode code points to be drawn to the screen and go from there. Ideally, the simplest procedure you can think of probably goes something like this. We keep a map of Unicode code points to corresponding individual glyph drawing information. We initialize a cursor on the screen where we want to draw the text, then iterate through the code points in our string. Draw each one and advance the pointer by the width of the character. In an ideal world, this would work, but this is text rendering we are talking about. Of course, it isn't that simple. The issue is, different scripts work with text very differently. The Latin script is pretty easy, but when involving scripts like Arabic, Devanagari, Kanji, and the rules of writing change dramatically. And even within a single script, different languages can sometimes use different rules or use different characters and so on. To overcome all of these differences, an input string of text first goes through a process called text shaping, using something called a shaping engine. There are several passes that happen in text shaping, and these are generally based on the script that you are working with, defined by the shaping model of that script. For example, here's the shaping model for the Devanagari script. You can classify these steps into three major parts: substitution, reordering, and positioning. Let's talk about what these are exactly. The substitution operation replaces a set of code points with different code points. One place where substitution is required is with ligatures, where a set of multiple glyphs can be replaced by a single glyph that combines them together. For English, ligatures are not required, but other scripts like Arabic and Devanagari look completely wrong without them. Along with this, there are also contextual substitutions, where glyphs take different forms depending on where they are in context with the rest of the string. For example, the Greek lowercase sigma has a different glyph based on whether it's at the end of a word or not. Finally, there's also aesthetic single glyph substitutions for characters like the ampersand. Of course, I haven't covered all the possible cases where substitution may be required, but if I did, we'd be here all day. I've linked all the resources I used in the description so that you may check them out yourself. Next, we have reordering. This operation is useful when the location of a code point in the Unicode string doesn't match exactly with the glyph in the visual order of that string. For instance, the E vowel in Devanagari can be combined with any consonant, in this case K, using these code points. But you can see here that the modifier appears on the left of the consonant, so you would want to reorder the code points before drawing. Finally, we have positioning, which is exactly what you think it is. Sometimes, in certain contexts, glyphs may need to move slightly from their original positions. The simplest example for this is kerning, where for specific pairs of characters, you can move them closer than normal because they just fit better. For example, AV. Another place where positioning is pretty much required is in any cursor font, where the end of the character should match correctly with the start of the next. Positioning also heavily depends on the script that you are working with. All scripts have a certain directionality. English goes left to right, then top to bottom. Arabic goes right to left, then top to bottom. And traditionally, the three Japanese scripts go top to bottom, then right to left. So, the positioning operation also takes this directionality into account to place characters correctly. That's it for the text shaping operations. Given a shaping model and some text to shape, you can figure out positions and the exact glyphs to be drawn. Of course, in this case, doing all of this yourself can be daunting, so libraries like Harpers and Uniscribe implement text shaping for you. But in my opinion, it's always good to know how something works and why it's necessary. Finally, to put everything together, we take the glyphs and the positioning data we get after shaping and use one of the four techniques to render the glyphs at the right position. And here we finally have complete text rendering. I hope that this video was able to show just how complicated a seemingly simple topic can get just by trying to support more and more features. However, even if text rendering may seem daunting now, the reality is that 99 times out of 100, there are certain constraints that you can and should impose upon yourself to simplify your implementations. Odds are this small 2D game that you're making won't need to support 100 languages with all sorts of directionality. Using simple bitmap fonts and assuming English only is not an invalid decision, rather, it may be the right one for you. Making these concessions in the right spot can make or break your projects and hopefully prevent you from going down unnecessary rabbit holes. Anyways, one last thing. Throughout the video, I talked about many graphics programming concepts, and to truly understand those, a good understanding of maths is very required. So, for that, I want to quickly talk about today's sponsor, Brilliant. Brilliant has thousands of interactive lessons for programming, maths, data analysis, and more, and is a learning platform where you learn by doing. It helps you develop your critical thinking skills by giving you actual problems to solve rather than memorization, which I respect quite a bit. And it's also a very effective way to actually learn topics since that content is created by professionals from MIT, Caltech, Microsoft, Google, etc. I highly recommend their math courses specifically since they cover topics from the very fundamentals like building and using formulae for different scenarios all the way to linear algebra and calculus, all of which are genuinely super helpful when graphics programming. So, to try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/voxoriffs or scan the QR code on the screen or click the link in the description. You'll also get a 20% off on an annual premium subscription. Thanks a lot to Brilliant for sponsoring this video, and thanks to you for watching. See you next time.